here's the thing. Here's 2 dimensions, everybody. We are on 2 dimensions on this board right now. I'm doing 2 dimensions right over here. If I just draw a vector right here in 2 dimensions, if I want to draw a vector that is perpendicular to it, I could do this, and it is perpendicular, right? Or I could find this one, and it's what? Perpendicular, right? The problem now that we ran into with that question before, and thank you for fixing this, Tame, is if we're suddenly in 3 dimensions, what could I do with this vector? I could swing it out, correct? I could swing it out. So for example, put your arm out right here. I could do a vector that's perpendicular to it, right? Is it perpendicular? Sure. Is it perpendicular? Is it perpendicular? Yes, okay. Now imagine there was a plane. Keep your arm out for a sec. Imagine there's a plane right here. Ready? Everybody sees the plane right here? Everybody sees it? Is this vector perpendicular to the plane? Sure. Is it perpendicular to the plane? No, but is it still perpendicular to this vector? Yes. It is. So what we did was we found one of the infinitely many vectors that are perpendicular to that vector, but if you turn it, Jesse's like, this is kind of weird. I get it. If you turn it, it's no longer perpendicular to the what? Plane. So we just got a factor that helps us out tremendously because we haven't done cross product yet. This helps us out tremendously because if we go back to that question, I'm just going to trash this here because it makes it, we were fixed in 2 dimensions right here. So I'm going to go like this. Whee, like this. See this, everybody? I'm going to go away. It's going to go away. Kind of should make you feel a little bit better. Just redoing it. Mistakes happen. Absolutely. Take a look at this. Is this almost in the right form? What do we have to do to this to put it in the right form? Subtract 2, right? So what do you end up with? You end up with minus 2 is equal to 3x minus y minus what? Z. So the perpendicular vector is going to be what? 3 comma negative 1 comma negative 1, right. Why doesn't it matter what the constant is? What happens to the plane if you change this constant? Nothing. If this is just negative 2 or 12 or a billion, all the perpendicular vectors are the same. It doesn't change the set. If I just change the height of a slope, does that change the vectors that are perpendicular to it? No. So if this is the perpendicular vector, it leads us to an easy one for find a vector that is parallel to the plane. How do you find a vector that's parallel to the plane?
You can just find a vector in the plane, for example.
Are you with me so far, everybody?
Yes.
So you have some ramp, you have some object maybe moving on it, right? And this is eventually this is going to represent the force pulling the object up the ramp. V parallel plus V perp is equal to V. We know just through basic trigonometry and basic cosine and sine values, the magnitude of V parallel, the length of this, is equal to the magnitude of this times cosine of theta. Are you okay with this truth? This is the first one. Are you okay with this?
Yeah.
The length of this vector is equal to the length of this vector times cosine of this. Are you okay with that right there? What is cosine? Cosine is opposite over what? Hypotenuse. That's where you get it from. Okay, let's keep going here. This vector right here, V parallel, this is a vector. This is no longer a magnitude. So if we know the magnitude of a vector and the direction it's going in, if we know the magnitude of a vector and the direction it's going in, can we write the actual vector? Yes, because U is always going to be what type of vector? What does U stand for? Unit vector. If you multiply something times a unit vector, does it change the magnitude? No. So the point is this. This is the magnitude we want, and this is the direction we want to go in. So V parallel is this magnitude times that direction. As long as you have the direction in what magnitude? Unit vector. Are you with me so far? It has to be a unit vector. Well, here's the thing. What's the magnitude of a unit vector? 1. So what's the difference between this line and this line? What's the only thing I added in right here? The magnitude of U. Am I allowed to do that?
Yes.
Sure, because what's the magnitude of U? 1. So are you okay with this line right here? Does this look, ignore this. Does this look familiar right here?
Yes.
What is that?
Dot product.
That is the dot product between U and V. So you replace it with the dot product of U and V. This is one thing you're going to have to memorize, which is V parallel is equal to U dot V times U. If you want the component of V going in the U direction, you do the dot product of the two, which is a scalar, and what's that? The direction you're going in. This is really important because when we start moving objects around, we're going to want to know how much work is done to move the object. We're going to need things like this. Do you understand the algebra so far? That's all I'm asking, not the application, the algebra. So the last two truths here, if V parallel plus V perp is equal to V, what does V perp equal? V minus V parallel. This is really important stuff. So once you find V parallel, what do you automatically have? V perp. Sit down, everybody. You just know that the magnitude of the wind is going to be the magnitude of whatever that vector is, F. Everybody with me? So if you want the magnitude of this vector, it's the magnitude of F parallel is equal to the magnitude of F times cosine. This is what we just did. We good so far? What direction is the boat going in? Which is the U direction, which is also a unit vector, yes. So you add the vector component onto this and you get F parallel. You get F parallel right there. So what's the degree measure? 30 degrees. Well, can you do cosine of 30 degrees? Hopefully, that's root 3 over 2, right? So what does this tell us? It tells us when you do this, when you know F parallel, oh, can you add in U here? Oh, that's the dot product right here. If you add this in, what do you end up with? You end up with F parallel is equal to root 3 over 2 times the magnitude of F times U. What this can tell you is what's the force vector going forward. So if the wind is, do we know what the actual force vector of the wind is?
No.
No, but do we know how much force is being exerted forward in relation to that?
Yes.
What's root 3 over 2? Anybody know what root 3 over 2 is? In decimal form?
Probably be
0.87? So 0.87-ish?
Probably 0.865.
865, rounds to 0.87, I think. But here's the thing. If this is 0.87, what does that tell you? If the wind is going at a certain force this way, what's the force going forward? 87% of that. So there's roughly a 13% reduction in the amount of force. Are you with me so far? So the force going in the direction the boat is going in is 0.87, rounded, of the force of the wind. You've probably done questions similar to that before. Right here, this picture right here is exactly the same as the one we had before, but instead of this V vector, we're going to call it the force vector. So I'm pulling something up a ramp. I'm pulling something on the floor, but am I pulling it in the same direction that it's going in? No, I'm going to be pulling maybe up a little bit. Like if I'm pulling a cart, or I'm pulling something that's rolling, am I pulling it straight forward? No, I'm pulling it at an angle. So what do we have here? If we want to know the magnitude of F parallel, hey, does this look familiar right here? Have we seen this line before? Exactly the same as what we had before. Okay, that's nice. Work, the definition of work is how much force you're exerting times the distance you're exerting it for. Force times distance. Are you with me so far? So the displacement here, if we want to do displacement, it's going to be right here. Right here, it's the magnitude of this. So what do we end up with? We end up with, take a look at this.